Christos Christodoulopoulos, who's going to give his pre-guided talk.
Thank you. Okay. I'm going to start talking about a paper that Mark wrote a couple of years ago, which is called Romantics and Revolutionaries, Smart Theoretical and Computational Linguists Need to Know About Each Other, but we're afraid to ask. And we are the revolutionaries, by the way. Yeah. And in that paper, Mark touches on a really interesting point, which is that theoretical and computational linguists don't really talk to each other as much as they should. And okay, this might be an overgeneralization, but I think part of the problem is that we're not really doing linguistically interesting, at least, stuff. We're mostly focused on supervised models, so we already have the annotation from the linguists. We're mostly focusing on English, well, if WHA sections 2 to 20 don't count as English in general. And we're mostly ignoring the sort of long tail of Zipf's law. So we're doing sort of the really frequent stuff. And I think what was right in calling us revolutionaries is just that I feel like we need a bit less supervision. So apart from the obvious problems with supervised models being that they're very expensive to produce and that we can't reproduce them from languages that we don't have enough resources, I think the really interesting property of unsupervised models is that they're really good at spotting patterns. Especially with the recent advances in machine learning, we can basically pretty much guarantee that with any amount of data, we'll be able to find something, some form of patterns that will be, perhaps might have been missed from traditional reviewing of the data. Unfortunately, they're not really great at looking at the whole picture, and this is probably because we've been using this notion of the pipeline approach. So everything is compartmentalized and sort of bleeding into each other as serialized tasks. And every sort of researcher would be focusing on one, maybe two of these tasks. And what I want to do is challenge this pipeline approach and have the tasks sort of interact with each other and talk to each other in interesting ways. And to give you an idea of the scope of the problem, here is some example works for each area of each sort of direction of the two tasks. So these are actual systems using input from one task to the other task. There is only one joint model in this diagram, and I would argue that it's perhaps between the two easiest of the tasks. And I'm interested in what's missing from this image, namely the other sides of the arrows. We need to make these tasks talk to each other bidirectionally instead of unidirectionally as we've been focusing so far. So this will be part of the main focus of my thesis, which starts by positing that there are patterns to be found in text that might correspond to syntactic categories or morphosyntactic categories, or part of speech, that don't necessarily correspond to any traditional notion of part of speech, but nonetheless will be motivated or influenced by what the linguists have to tell us about part of speech. I will be using this, I will be breaking down the pipeline paradigm to have a holistic view of NLP, sort of allow all the individual components of the NLP pipeline to talk to each other and produce, in the meantime, produce a better notion of part of speech. And I will show that we can do this in a computationally efficient way. And all of this will lead me to produce cross-lingual clusters that will be useful, perhaps, to give us new linguistic insights, but more importantly, I will show you a way of producing those clusters. So here's what my thesis will look like. So lots of people ask me this question. Is there a way that we can have a system produce clusters of words that correspond to morphosyntactic properties in a language? And is there a way that we can have those clusters between two languages linked, aligned in a way that will provide some interesting patterns? And is there a way that the types of clusters that we find might be influencing the types of links, the types of alignments that we have between those languages? Well, the answer to all those questions is yes. This is actual output from my system. Well, this is actual output from my system. There's lots of alignments there, lots of links to be found. Yeah, 3.5 years for this. It's worth waiting to see this whole picture. I will return to this, this picture later on and see what sort of analysis we can have from this. But first of all, I want to tell you how I got to this picture, how I produced this output. So what we need is, first of all, we need to know what we're looking for. We need to see what the theory tells us that we should be looking for in the part-of-speech literature. Then we need something to actually produce the clusters, influenced by the theories in so far as to combine multiple sources of information, which is what the consensus, at least, of most theories seems to be. I will also be reviewing some of the existing methods of doing part-of-speech and see what key insights we can get from the literature. And finally, to get that picture, we need to have an alignment method that is influenced by the type of clusters, the type of part-of-speech that we are producing in each language. Okay, let's start with the first one. There doesn't seem to be a lot of agreement in what people think part-of-speech are. People don't even agree what to call these things. Like, some people call them syntactic categories, some people call them word labels, part-of-speech. There's one thing that most theories do agree on, and that is that they need to capture more than one, what I call levels of language. To give you some examples of theories and what I mean by the levels is that even from the very beginning, people were talking about semantic and morphological definitions of part-of-speech. Dionysus was talking about all three, semantic, syntactic, and morphological rules in order to find part-of-speech. Lily Murray, who gave us the modern view of what we consider the classic sort of 9 part-of-speech, was talking about semantic and syntactic rules. Ray Gackentop is an exception in this. He was talking about mostly purely syntactic criteria. And so was Susan Schmeling, although she was approaching it from the other side. Wish there was a way of combining those two and get syntactic and semantic. That would be fun. And then we have people like Paul Schachter, who was talking about a cognitively plausible, like pragmatic view of part-of-speech, even though he admitted that we need to use morphological, syntactic, and distributional heuristics to get to those parts-of-speech. So the overall conclusion, even though it's not really easy to pick one theory and say, okay, we can do this, that's what we need to model, the consensus seems to be that we need to have to be able to combine multiple sources to get to the best notion of part-of-speech that we can. So that's what I'll be taking from these theories. Yes. Okay. And here is how I propose we do this. First of all, I'm going to talk a bit about how we're going to know that we have good clusters once we found them. So before I talk about a review of existing systems, I'll talk a bit briefly about evaluation. So there are two ways of doing evaluation in this task. One is intrinsic, so basically test on data that has been annotated by some experts and test against those. And the extrinsic way, which is just to use the output of the clustering system as an input to another task and then evaluate that other task. So there are problems with both, especially when we're dealing with unsupervised models. And I'll talk a bit about the problems that we can find in both kinds of evaluation. So for the intrinsic evaluation, one of the main problems is that the clusters might not necessarily correspond to the traditional notions of part-of-speech that we have. First and foremost, because the clustering systems will just produce random cluster IDs instead of labels. They won't produce noun or adjective, they'll just say cluster 32, cluster 31. And then the other problem is that there might be different sizes of clusters. So instead of just the 9 or 10 parts of speech that we're looking for, a system might produce 1,000 clusters, which might be a bit difficult to map back onto the 9 clusters. Another problem is that gold standard annotators might follow a specific linguistic theory when they're doing their annotation. So perhaps one of the series that we saw earlier, or any other different theory, and this is mostly because they're using their annotation to tune to a specific task. They have a specific task in mind. So in part-of-speech, in case of part-of-speech, they might be thinking of using the part-of-speech as input to a syntactic parser to make the life of the syntactic parser easier. So they will have tuned their annotation to accommodate that task. And we might not have the same task in our case, or we might be using a different task, or not any task at all. We might be installing just the clusters themselves, as I However, the biggest problem of intrinsic evaluation is that we're trying to find clusters that might not correspond to gold standard notation, and then we're trying to evaluate using that gold standard notation. So it's a kind of a cyclical problem. And in the literature, many people just ignore the issue and use intrinsic evaluation anyway, or they use extrinsic evaluation instead. My solution is to test on multiple languages using multiple systems, so multiple annotation schemes, in the hope that there's bound to be some overlap between some of the annotation schemes in some of the languages with what the system finds. So basically, the more languages we find to test, the more likely it is to capture something that the annotators would have captured. So the other kind of evaluation is extrinsic evaluation, which has its own problems. First and foremost being if the second task that we're annotating is itself intrinsically evaluated, then we're just passing the problem along. We have the same issues that we had in our intrinsic evaluation. Another problem is that the performance between the two tasks might not be correlated. So if we have task 2 having its intrinsic metric saying, yes, we're doing really well, and task 1's intrinsic metric says, well, we're not doing that well, which one do you believe? Like, it's not necessarily that they will have the same response. And part of the problem, of the second problem, is that not all of the second task's input will be the output of task 1. So if we say we're doing syntactic parsing, part of the input might be the part-of-speech labels, but part of the input might be the words themselves, might be some morphology information, who knows? It could be lots of different sources, so the effect that the output of the first system has is limited, basically, to the extent that is input to the second system. Okay, so an overview of what I'll be using for the rest of the talk as evaluation metrics. I'll stick to intrinsic evaluation. I will be referring to extrinsic evaluation, but mostly as a sort of way of confirming what the intrinsic metric tells me. There are two ways of doing intrinsic evaluation: mapping metrics and information theoretic metrics. Mapping metrics is simply what the name implies. You just map the cluster IDs to a specific label, and then you just test for the accuracy. So cluster 31 might be nouns, and then you test if that cluster only contains nouns. They're very widely used, pretty much until very recently. That's all what the literature was using. However, as I have shown in my review, but I will not show here, they are quite sensitive to the size of the induced tag set, with the extreme case being that if you have one word for one cluster, then the score is 100%. Basically, you get the best score. The other way is to use information theoretic metrics, which treat the two different groups of clusters as information-bearing units, and then they compare the relative entropies or the conditional entropies and get a score out of that. They're less sensitive to the size, both the size of the induced cluster and the gold standard clusters, tag set, sorry, but especially in the case of variation of information, but I would argue both of them are less intuitive to interpret, because at least with the mapping, with the minute one, you can actually see, okay, yeah, cluster 21 was a noun cluster, and there are lots of adjectives there, so that's wrong. Whereas with cross entropies and variation information, you can't get the same sort of exact feeling of what's going on. Nonetheless, I'll be using both minute one and VM, just to give you a good overall image of what's going on. And I'll start with this big evaluation introduction, and give you a short story, condensed story of my review of existing methods, which has been contained in my 2 papers on the subject. That initialism means too long, did not read. It's from message boards or something. So if for people who weren't interested in reading the paper, I'll give you sort of the skinny. So I examined lots and lots of systems spanning like 40 years worth of research on clustering methods, mostly focusing on the sort of later machine learning models. And what I found is, first of all, in my 2010 review, which didn't contain all the systems there, but what I found was that it's not necessarily true that the more advanced systems will perform better, especially in the case of the system by Alice Clark and the system of Brown in 1992. They're actually the first and third best performing systems of all. And if we compare them to the other systems, so Clark is still performing well, however it is being superseded by the two more modern systems that I've tested. Apart from like the relative scores and the performance of the state of the art of the task here, what I was interested in my review and what the main outcome of my review was the properties of those systems that sort of were performing the best. And the two most successful strategies were, first of all, to use morphology as features. So that has been the key to the success of most of the systems in this, the newer, at least, systems and Alice Clark system. And then the other property that was very successful indeed was the use of limiting one cluster per word, so basically not allowing for ambiguity. So can the verb and can the noun will be clustered in the same cluster, basically. No ambiguity is allowed. So having these two properties in mind, these key insights in mind, and having a baseline sort of a feel for what the area is doing, I went on to define my own model, which would allow me to combine, as we found from the linguistic theories, to combine multiple sources of information. So I call it the Bayesian multinomial mixture model, and it has three key properties. One of them, as we saw from the review of the system, is this one tag per word constraint, which does limit the ceiling performance. Basically, it won't ever let us have 100% performance because we're missing the ambiguity. Although, as it's been found, at least in English, the ceiling performance that we get is 97%, at least in WSJ, which is not a bad performance to get. And so, especially for the unsupervised case, for my case, it's very, very useful to have that constraint. The other property is that it's a mixture model instead of an HMM, of a sequential model, and that makes it easier to incorporate non-local features, as I found, which in turn makes it easier to add all the features that I'm interested in, namely morphology and alignments, and I will be adding dependencies by the end. So, let's see an overview of the generative story of the system. We have here, for each word type, which includes many instances of that word type, we will choose a class or a cluster for that word type, which is conditioned on a prior distribution theta. And then for each token of that type, we'll just emit all the different features that that type is associated with. So in this case, we have one single feature per word token, and that could be the word to its left, or the word to its right, or something like that. And it's easy to see how we can extend this type of model if we assume that all the features are conditionally independent. So here we can have different token level features, such as the left and right context words, the word aligned to this word in a different language, or for instance, the syntactic dependency of this word, if we want to. And then we have type level features, which in my case would be the morphology features. So all the tokens of a specific word would have a specific morphology signature, let's call it. So it could be the prefix or the suffix of all those tokens. So here's how the model performs. These are developmental results averaged over 8 languages. So I'm not comparing with any other systems yet, but just to show you how the different components of the model work. So here is the baseline score for the model, and then if we add the morphology features, we get a nice boost in Merit 1. VM doesn't perform in the same way. At least one of the metrics agrees that morphology is indeed useful. If we add the alignments as features, and if we allow for any of the 8 languages to be aligned with any of the other 7 languages, and we take the average score of that, we see that alignments actually hurt the performance of the model. But if we know which one is the best language to align to, performance does improve. quite dramatically. However, this is a kind of an oracle result because we do need to know which one of the languages is the best to align to. So for the next comparison to the state of the art, I will only be using the morphology model. And here are the two winners of my two reviews, just to give you an idea of the comparison with the state of the art. And here is the performance of the BMMM. There is no significant difference between the performances of this model, even though numerically the BMMM does outperform both Clark and the HCD model. However, this is good news because all it means is that it's on par with state of the art, and we have now a model that would allow us to have these multiple sources of information. So we're doing okay, I think. So having got that model, it's now time to go to the final step. However, if you've noticed, all the information to the part-of-speech task is going into the part-of-speech model. And I talked about sort of breaking the pipeline and doing the bidirectional thing, and I haven't shown you a way of doing the other direction. So everything was going in, but not going out. So before I go to the alignments, I'll talk a bit about how to get to this bidirectional, get the bidirectional information from the different tasks. This idea basically came to me when I was trying to add dependencies to my model. And I thought I'd use the DMV model of Klein and Manning, which is basically the single most successful model, and it's been the basis for pretty much every dependency parser that's out there, and lots and lots of people who use this. And has one key property, which is that it uses part-of-speech, gold standard in the 2004 paper, gold standard part-of-speech, instead of words, so it's unlexicalized. And that gave me an idea, which is, what if we have part-of-speech that would help the DMV produce better dependencies, which would then be feed back to the BMMM model that helps us produce better part-of-speech, and then just do the thing again and again. So that would be a nice proxy for a joint model instead of actually trying to induce both of them at the same time. So here is the what I call the iterated learning model. We start with the basic BMMM. It might have left and right features, it might have some morphology features, but crucially not dependency features at this stage. And we feed the output of the BMMM model to the DMV. DMV does its thing, induces the dependencies, and then we call this whole thing one iteration. And we treat it as a sort of black box, and we get the dependencies out of it. We get it as features into the second generation now of the BMMM, and we just repeat the whole thing again and again. So I'm going to show you some results, first of all in English, and then averaged over the 9 languages of the CoNLL dataset. One crucial detail is that the DMV model here is the sort of the weak link, because it is very slow to produce the dependencies, and as it was usually in the literature, until very recently, that is, people have been using less than 10-word length sentences. So we're limited basically by the DMV in this. So at first I'll only show you results for less than 10 words. So here are the results in English. We see a very nice curve of the speech induction model increasing its performance with successive iterations. The DMV model follows suit, which is very nice. We can see that most of the gains are pretty much until iteration 5, so for the rest of the experiments that I'm presenting, and because it is very, very time costly to produce these models, I will only use up to 5 iterations. So here are the average results on the CoNLL dataset. We can see that now, averaging over the 9 languages, we can get a significant improvement by the time we hit the 5th iteration. However, the difference in the DMV score is not significant. Interestingly, if I compare these to the scores of the systems that use the gold standard information, respectively, so the part-of-speech model that uses gold standard dependencies and the dependency model that uses gold standard part-of-speech tags, we can see that for the part-of-speech model, we're very close to the performance of the gold standard dependencies model. but not for the dependency case. So we can do much better in the dependency case. We can produce basically better clusters for the dependency model. There are two shortcomings, obviously, in this model. First, DMV basically is not anymore the state of the art. It's been superseded pretty much by every other dependency model by as much as 15%. I've seen, at least in English. So the other problem is, again, related to the DMV, that we're limited to this 10-word sentence limit. So it makes it hard to compare with other partner speech inducers because they're not limited by anything. They just use full-length sentences. And it's actually not very realistic. We're interested in actual sentences that might be useful for linguistic analysis, and no one actually speaks in less than 10-word sentences. So the solution to the first problem is just simply replace the DMV components with a better model. I chose the two-substitution grammar DMV version by Phil and Trevor, and I'm not going to show you the results, but the short story is that we do get a performance boost in the part of speech component. However, the dependency does really badly, and it gets worse with every iteration. And I have some possible explanations, but I'm not going to steer the discussion away from this. But it's really interesting to see why it's actually doing this. For the second problem, again, the solution is easy. Just wait it out. Like, use full-length sentences and just compare on full-length sentences, basically. So this is what I'm going to do. These are the scores of the 10-word case, just for comparison. And here is how well we do for the full-length sentences. Firstly, the performance of the DMV has dropped, which is normal, is to be expected because there's like much more ambiguity now. However, we do get a significant increase now from that very low initial score to something that is quite close to the performance of the 10-word based model. The part of speech does, again, very well. The base performance has actually increased because there are more words, there are more data to go through. And we get a significant performance boost in both the first step and by the time we hit the fifth step. However, the most exciting news are the comparison with the performance of the gold standard based models. So for the dependency case, we basically have reached the performance of the model with gold standard power speech, which is really cool. But more exciting is that we've surpassed the performance of the model with gold standard based dependencies. So basically, part of speech, the part of speech model is making the best use out of the dependencies that it gets from the DMV, which is really exciting. So to recap, we've seen that both in this iterated learning framework, both the DMV and the BMMM models do improve, mostly in the first few iterations. And by using full-length sentences, we do increase the performance of the part of speech inducer above the baseline, above the system with gold standard dependencies, and the DMV is getting closer to its theoretically sort of peak performance with using gold standard part of speech, but it's still a bit lower than the 10-word case. So now we've talked a bit about how to get the bidirectional sort of side of things, and now we can finally go to the last step of our roadmap, which is, now that we have a way of getting information to the other tasks, let's use them to get to the task of alignment. So for this, I'm going to be using Giza. It's a fairly well-known model, and it uses a notion of word classes to condition its alignment probabilities on. I'm going to be basically hijacking that module and replacing it with the BMMM. So basically now I have an input. I have a hook in that model, and I can use it for my bidirectional way. Because if you remember, the BMMM was already using alignment, so I had one sort of channel already there. So I will be showing you results in two corpora. First of all, the French and English corpus of the Hansards. I'm mainly using this because there are some manually annotated alignments there, so we can see the performance of both systems. And also I will be showing you results in the multi-thesis corpus, which is just 7 translations and the original novel of 1984 by George Orwell. So, for the French and English, we can see, even though it's a bit more bumpy, the performance of the part-of-speech component does indeed improve over the iterations, from the baseline at least. And we can see that the performance of the alignment model does indeed seem at least to follow the performance of the part-of-speech component. So basically, the better tags we give it, the better the model does, which is to be expected. However, the alignment model seems to be sensitive to the size of the corpus that we give it. So basically, the more words it has to process, the less it relies on part-of-speech information. So if we double the size of the corpus that we use for the alignment, we see that the response of the alignment model is a bit flatter. It gets a bit flatter, even though the performance of the part-of-speech component does seem to follow the same trend, the same growth as before. And this is the performance in the multi-thesis. Remember, we don't have gold standard alignments here, so we can only evaluate the part-of-speech bit. We do not get a significant difference by the time we hit iteration 5. However, the most important component, the most important part of this is that we have now a way of getting the alignments influenced by part-of-speech and vice versa, and it's not doing worse. So that's something. So to recap, I showed you the iterated learning model, how it can be used between any two tasks, between part-of-speech and any of dependency alignments. I haven't shown you morphology, but I have used it to induce iterated learning morphology segmentation. I do think that this is an effective proxy for joint inference instead of actually doing a full joint inference. And I've shown you that part-of-speech induction does seem to be helped by all the other levels that we feed it. And I think this is a good test for theories of part-of-speech. Basically, if a theory of part-of-speech tells us that morphology is key to identifying part-of-speech, this is a nice way of testing it. Or if syntax is key to a theory, this is again a nice way of testing these theories. But more importantly, this for me proves to be a good way of having a joint model for all of NLP, basically. Every task we can think of that could be influenced by part-of-speech is basically able to get into this proxy for a joint model that I have. So I've shown you bidirectional interactions between any of two tasks. Well, what's stopping us from going a bit further than that and actually doing this for all the tasks together? So this is what I meant by the joint model. And how I'm going to do this is what I call induction chains. So in the beginning, we had these sort of linear going from part-of-speech to any of those tasks. Then I showed you a way of getting them sort of into a loop kind of framework, which allowed me to have any of those two tasks basically be learning as a joint model. And then the obvious extension is to have all of the tasks interacting with each other in a sequence of inference steps. So we can choose one chain from this lattice. So we can say we start from part-of-speech, we go to dependencies, then we go to alignments, then we go to morphology, and so on. Or we can choose another chain, which is to go from morphology, then to dependencies, then to alignments, and so on and so forth. With the part-of-speech being the key component that connects all the tasks together. So here are some results on this. I'm only going to be showing you development results that I have between English and Bulgarian. So basically the alignment is between those two languages, Bulgarian to English and English to Bulgarian. These are my baseline models, and I'm going to start by showing you the first type of chain, the first sort of permutation in this chain sequence, which is to go from alignments first, then to dependencies, then to morphology. And we can see that while for English it seems to be a nice model, for Bulgarian actually, even though I should say both chains are significantly better than the baseline, for Bulgarian at least performance seems to go down, so we should at least try and see if any other of the chains are any better. And indeed there are some chains that do perform really, really well. Especially, I want to draw your attention to the last chain, which is morphology, dependency, alignments, and which follows the kind of hierarchy of complexity that we might have in our mind. So we start with morphology being sort of the simplest of the tasks, then we add the syntax, and then we'll go to a different language and align them. For Bulgarian, this is by far the best chain. It produces, by the end of the 3 steps, it produces the best results. And even though in English the alignment step seems to actually drop the performance, that could be one theory that I have is that Bulgarian is not the best language to align English to. As I showed you in the results in the BMMM paper, there are some languages that basically are more attuned to be aligned to. So for English, at least in my 2011 paper, I found that Czech is the best language to align to. I don't know why. But even though there is this drop in performance, by the time we hit the last step, we still get the best performing chain, at least on par with the best performing chain, even in English. So I'm going to stick to this chain and finally get to the last step and get back to my image of my thesis. Oh, yes, before I go to that, we do need to think of what we're going to be analysing. I've talked about how it's really nice for linguistic insights and how it's really good to have multiple languages and everything, but I think that we need to have a really big parallel corpus to do our alignments and to do our analysis on. So what I did is I collected lots and lots of translations of the Bible, which is the single most translated book in the world. I semi-automatically cleaned them up and I aligned them according to the CES standard that was used by Philip Resnick in his own Bible corpus. But instead of 13 languages that Philip had, I have now 100 languages to work with. So even though I will not be presenting results from all the languages, mostly because I don't speak any of them, I've created this corpus as sort of a tool and a help for the kinds of analysis that I am interested in. So here is a map of what the languages look like, where I got them. I tried to try and have more than just the basic Indo-European languages, so we have more interesting linguistic phenomena to study. Okay, so finally we get back to this image, and now I can tell you a bit more about the kinds of analysis that we get once we know how to get to this picture. So I'm going to give you the translations of the Greek so that you can follow along. So one example of the kinds of structures that I do get out of this is this blue cluster that I found in English, which is basically just the infinitives, aligns with clusters 8 and cluster 32 in Greek. So cluster 8 contains mostly third-person present tense verbs, and you can see why the alignment is there. If we have a sentence like she wants to make, in English it will be expressed by the infinitive. However, in Greek you have to have the third person marking there in the verb kami. So to me this implies that there is this sort of hidden third person aspect to the infinitive. So the infinitive actually means she wants for her to make something. So there is this aspect of the third person there, but it's hidden, but it can be captured by this sort of cross-lingual clusters. And then the other interesting phenomenon that I found was the case of the subjunctive mood, which in English is distinguishable from infinitive, and even though it's very rare, remember this is biblical text, so it's kind of an archaic version of English. And even though it's rare to be expressing the subjunctive mood like this in modern English, my cross-lingual clusters do capture the fact that this cluster in Greek does overtly, morphologically express the subjunctive mood. So it's really quite exciting to see that the same cluster in English is basically a mixture of clusters that do express what the infinitive does and what the subjunctive does in Greek. So this is the sort of analysis that I am interested in basically, but there are more qualified people than me to do this. This is sort of a way of getting, I would say, getting linguists to be interested in what we're doing. I've presented a way of inducing syntactic categories from raw text. I've talked about how the different theories of syntactic categories influence our decisions, and I've just reviewed existing systems and existing evaluation metrics to know how well we're performing on this task. I showed a way of doing away with the pipeline model and have all the NLP tasks interact with each other and help us to induce multiple levels of linguistic structure at the same time, which allowed me finally to have this idea of cross-lingual clusters, which I think is a very interesting tool for linguistic inquiry, and might potentially help us find similarities between clusters across languages, and the sort of analysis that I did for English and Greek. So, one final slide. What are the future directions that I see with this project? First of all, it might be interesting to see a fully joint model developed if there are ways of joining those tasks with a single objective, basically, and have a single learning, a single inference. I showed preliminary results for joining the speech independency tasks in my thesis. However, there's still a lot of way to be done in this. Second, the evaluation methods. I still can't get over the fact that the evaluation that I used was inherently cyclical, and in a way we should be able to make it without using gold standard orientation. So Noah Smith proposed a very interesting, in my view, approach. However, it's still there are lots of issues with his proposal. I do think it's a very interesting direction to work with, and I do hope that more research has been done in this area. Finally, what I'd like to call syntactic and aware clusters would be nice to be found. So something like the CCG types, that once you identify the cluster, it then knows what sort of syntactic structure can be used in, and semantic structure. So Jonathan Besk and Julia Hockenmeier have done some preliminary work in this. Their system uses some prior knowledge in it, and it would be nice to see if we can do this completely unsupervised. And I'll just leave you with this sort of thought that I feel like we should be talking to the linguists some more, and I think that I hope that my thesis is a step towards that direction. Thank you very much.